So we'll start. So last time we talked about the product string. Today we were talking about the supergravity. In particular, so we will start with the 11D supergravity and then move to the type 2A and type 2B. And after that, we will go to the, so what was that? Let's see, 2B, 2A. Oh my goodness, I think it's better to write them. So 2, 1, okay. So 2A and 2B, depending on GSO projection, type 1 is oriented forward and heterotic O, heterotic E, and the 11D subgraph. And then that govern everything governed by M theory. So we will talk about so the existence of 11D supergravity strongly suggests the stronger coupling limit of the string theory, which is called M theory. Everything comes from this. It's now string theorists believe if you assume the M theory, even though it's not, there's a lot of mystery. Nobody understood the M theory, but if you assume the existence of M theory, you can explain many things somehow, and you can find something like a very novel thing, like a Lagrangian with QFT with a Lagrangian description. And also some duality and so on. So those are the something like that pops up once you assume the M theory. So we will talk about the 11D supergravity and M theory from now. Okay, last time I briefly explained the supergravity, but it was too brief, and let me explain a bit more. So supersymmetry is the essentially QA and then Q alpha and Q beta is equal to gamma mu alpha, which has the matrix alpha beta P mu, and it depends on the and then you can just again introduce sometimes people put I here and so on. And then if you can just use the E alpha, Q alpha for generator of the supersymmetry, Q beta. If you include this one, it becomes the I, E, gamma mu, E, and then P mu, roughly speaking. And this is the global version of the supersymmetry. This is global version. Global supersymmetry, which means the epsilon supersymmetric generator. The infinitesimal transformation for supersymmetry is independent position. So it's independent position, it's just constant. This is a constant spinor, constant spinor, constant spinor. So to make it supergravity, make it local, so gauging global symmetry. So which means the epsilon depends on the position of the spacetime. So then there is a corresponding gauging. So as you know, so gauge transformation for the gauge field, like gauge, usual Yang-Mills gauge symmetry. So gauge symmetry of the Yang-Mills is given by delta A mu is given by covariant derivative of lambda. This is the gauge symmetry of Yang-Mills. And then, but the gauge symmetry of the general covariance is given by as follows. So you have a spin 3/2 field alpha, which has the following property, alpha, and which depends on x. Maybe I should use the nabla. So this is covariant derivative. Of the space-time. I mean, the mu is, of course, partial mu plus a mu. Depends. I mean, physicists maybe put usually I here, and maybe sometimes some gauge coupling here. This is just a partial mu plus spin connection, or maybe sometimes people just say crystal Bell symbol, whichever you want, depending. And this field is called gravitino. Or sorry, gauge symmetry of the yeah, I think it is. Gauge field of general covariance. That sounds bit strange. Sorry. I think gauge symmetry or local symmetries. Local supersymmetry. Sorry. Local SUSY is given by here. And this is gravitino or Rayleigh Schwinger field. And it has spin 3/2. Spin 3/2. More precisely, this local supersymmetric transformation is given by, so if you have the phi bind or tetrad, you have maybe I should put the bar here. Seems like I should put the bar here. I mean, okay, it's okay. I mean, it depends on notation. Epsilon bar, gamma, m, gamma a, and psi m. So this is the psi m, and so this alpha, beta, maybe alpha bar, and beta. The spinor contraction is assumed, and also delta psi m is given by the covariant derivative of epsilon. That's exactly the same as before. So this is supersymmetric transformation for the gravitational usual the gravitational gravity multiplet. So this is spin 2 field, spin 2, that is spin 3/2. So then the action is usually given by dd4, ddx, and some constant 2 kappa d square, and then maybe square g, and then r minus 2I psi m. This is the usual form of the this is the supergravity action. So this is supergravity action. So R is the supersymmetric I mean, R is the Einstein-Hilbert action, and then the second term is the compensated for by Gravitino. So it's invariant under this supersymmetric transformation. It's invariant. If you can check that. I mean, maybe in my lecture note I put E here. E is equal to determinant of square root EM. I think sorry. Okay. So this is the usual form of supergravity action. And then the highest dimension of the supergravity, which has highest dimension of supergravity up to spin less than or equal to 2 is indeed equal to 11 dimension. So that's roughly speaking. So supersymmetry imposes boson and fermions degrees of freedom. Number of fermions should be the same. Number of that supersymmetry. Now, however, roughly speaking, fermionic degrees of freedom just grows exponentially, like this way, because fermions is a spinor representation. So it's spinor representation, so it's 2 to the some power exponentially. Remember, D is the dimension, and however, the gravity multiplet is always D times D minus 1 over 2 up to plus minus 1. Gravity, the number of degrees of freedom. So to match the degrees of freedom, V is up to 11. The highest dimension is 11. But if you go beyond that, you need to incorporate the spin like more than 2. And then, so 11D supergravity is uniquely determined. The action is given by as follows: 2 kappa 11 square. So S11D supergravity has the 1 over 2 kappa 11 square D11x square minus G, and you have the, I just write down only the bosonic part, and you have like a Chern-Simons type action, which kappa 4 K4. The subscript here is the number of forms. So this means 4 form, and then M is the 3 form. So the K4 is indeed equal to the field strength of 3 form. And moreover, so this K4 squared, this is equal to K4 wedge star K4 hot star. It's very like it's more like a kinetic term for K4. So this is bosonic part. Okay, bosonic. And then there is a corresponding fermionic part, but that comes from the supersymmetry. Yeah. So now the G R is coming from the gravitational multiplier GMN is 44 states, which means 11 times 10 divided by 2 is what? Why I wrote 54? 44, sorry. It doesn't look like 44. 5 times 5. Okay, 54. This is correct, right? Okay, so 54, I think it's typo.
No, sorry, it should be 10 plus 9.
Yo, 10 plus 10 times 9. You're right, you're right. It's you have to take a light cone gauge, sorry. Thank you very much. So this is d minus 1, d minus 2. Thank you very much. I was wrong. So 9 times 10. 9 times 10 minus 1 is 54. No, 44. Sorry for confusion. And you have these, and 3 is 3 form. 3 form is so that the, let's see, let's count. Let's see whether I can count correctly. 3 form, so that the 11 times is 11. No, I think 9 times 8 times 7 divided by 3 times 2 times 1. Is it correct? Well, what's this number? 84. 84, is it correct? 3 and 4. 84, good. I didn't make any mistake here, fortunately. So you have to take a light cone gauge. Okay. This is bosonic degrees of freedom. And if you look at the gravitino, the number of gravitino should be equal to to 100, and so the sum 128. Okay. So can anybody compute? Is it 2 to the something? It should be 2 to the something. What was it? Is it true? Huh? 2 to the 7? Good. 2 to the 7. Okay. And also, yeah, this kappa is related. So these are very simple. So and the number of Suzy is again 32. 32 supercharges. So you have 32 supercharge like this type. And also kappa 11 is just the Newton, almost like a Newton constant. Whenever you just use Planck length LP to the 9. So LP is a Planck length. LP is a Planck length, so that the it's written by h bar and g and the c cube. So this is Planck length. So this the coefficient over there is the 9 is actually light cone, the number of light cone dimension. Okay. 11 minus 2. So this is the Planck length. Yes.
So the degrees of freedom is 2 to the d minus 2 integrals, and this one should be 7 according to your classification.
Yeah.
And that would give you d of 14.
So this is d over 2, so it's 11 over 2, right? And you just take lower, I guess.
So it should be 5.
5. Good question. Let me think. That's a good question. That's a good question. How would it work? Why this is, should be 7? I don't have the good answer now on top of my head. Why it should be 207? Good question. To be honest, I don't know. Sorry. Let me think. Okay. So it should be 11. Why do I set the issue? So seems like in that case you have to more precisely. It should be add something here. It should be added something in that case. Let me move on. I don't have an answer on the top of my head. And then, so from 11D supergravity, one can create a so-called type 2B, 10D, type 2A, and type 2B. Supergravity can be derived by dimensional reduction. Sorry, 11. Supergravity can be obtained from the 11D to 10D to A. Can be easily obtained by dimensional reduction. So let's suppose we put the theory on S1 with radius R, and R when R is shrink to the like a very small. So then, so the metric 11-dimensional metric ds11 squared is given by GMN dxm dxn. So this is a metric, and then you just do the causal line. The one we did for T duality. So you just decompose. So M and N are runs from 0 to 10. Okay, 0 to 10, and here mu runs for mu and nu runs for 0 to 9. So that the third direction is a compact phi. Compactification direction. So that's theta is really the coordinate base one. And the radius is r squared, and but you just turn on some I mean, how to say, one form for of diagonal configuration. So it's more like a, so that's what I did. So what I did is this is g theta theta, and then here g mu nu, and then here's c1, and it's symmetric c1, like this kind of decomposition. What I have done. This is GMN. This is kind of decomposition. I think up to some scaling, scaling of R or something. I think I should put R here, maybe. Something like this. R squared, maybe R squared. Okay, so then we should do the same. So we have the graphton and three form and the graphitino. So we should also decompose three form as follows: M3 plus B2 which d theta. So this is three form is decomposed like this way, and also the field strength of the three form is also decomposed like this way. 3 which d theta. I mean, it's just a okay. D theta plus C1. So that they are related as follows. So H3 is it's more like a Ramon field strength. Oh, no, NSNS, sorry. I'm sorry. H3 is the field strength B field. So this B2 form is already B field that appear many times in string theory. And the G is the G4. So I define as the G2 and the G4 as the field strengths of Ramon. C is more like a Ramon. Okay. Sorry, 3. What I'm doing here. 1 and 3. Okay. So remember, so type 2A. So the reason why, so as I mentioned, so the supergravity is low energy limit of string theory. So you just only look at the massless sector. Okay. But the type 2A, so there's a DP brane. What is the P is even or odd? Well, what is it? Should be 2A is even or odd. Which one? Type 2A is P should be even or odd. Just tell me. Huh? Even, good. So this is coupled to electrically Cp plus 1 field. So the subscript here should be odd. So C1 and C3 is really Ramon. It corresponds to Ramon field, and G is the field strength. Okay. And then this G tilde is indeed just shift of the Ramon field strength minus so that they cancel. So essentially they cancel. The C1 H3 cancel with these guys. Okay. And what's left is indeed DC3 will give you G4, and DB will give you H3 and D7. Okay. That's just rewriting of the field. Okay. Then we can write down the action of the type 2a supergravity as follows. As follows. It splits into the two part, NS 2A and NS sector is 1/2 kappa, okay? Just a moment. Yeah. BD D10x and minus G, and you have the Einstein-Hilbert action, but it's coming from so this is supergravity NS sector. So as you know, NS you have the graviton and then B field. Sorry, B and then the diaton. So everything written in terms of this NS field, and then so Ramon is given by, again, 2 copper and square D10x minus square G, and then you just have a kinetic term of the Ramon field strength. Here, somehow you need to shift the field strength of field strength Ramon 3 form, so that it's a become 4 form, but you need to shift cleverly. And then you have the Chern-Simons-Term action. I mean, you can always. Yes,
It was minus in direction.
Thank you very much. So this is Chern-Simons type action. And thanks to the people like I don't know, to be honest, I don't know the history of supergravity, but I mean, people working on supergravity is doing a super tedious calculation indeed. I mean, you have to check this action plus harmonic field will satisfy all the supersymmetric variation. It costs like 10 pages to check supersymmetric transformation, but they would do that. They did that. It's really tedious. I know many people working on supergravity. They're super diligent people. One is my ex supervisor Bernard DeWitt in Netherlands. Anyway, you have to do the super tedious calculation to check supersymmetry is closed. Thanks to them, these actions are correctly supersymmetric. I never done that, to be honest. It's too tedious for me. Okay, and then now 2 kappa 10 square is indeed given by over 2 is given by, it's not a Planck length, it's given by the string tension, no, string length. So Ls is the string length as first member alpha prime square. Can you check my lecture note? I don't remember. Maybe there is some constant that will show up. I don't remember. Some constant show up, maybe. Alpha prime square, string length. Oh, yeah. I should have told you how that's. It's alright. So from here it's clear that I should have told you how the dilaton field show up. So from here it's clear that the M3 form you have the mu nu rho is equal to C mu nu rho. So Ramon's 3 form come from really this M3 from 11 dimension, and B field really come from M mu nu 11 dimension, which we call Saturn. Okay. From here it's clear, and also yeah, I mean, if you use a coordinate, the Ramon 1 form really come from the graph general metric. And then I should have mentioned that this G theta will give you the dilaton field. So more precisely, yeah. So more precisely, so if you do the following thing, you can check the following. So here, what did I write? Yeah, R. It's R. This R. So once you write this one, it's LP, Planck length square e to the 2 sigma. E to the 2 sigma, and then you just relate this R is e to the LP and e to the sigma. R is e to the sigma, and then we just rewrite this LP e to the 235. So we just relate this sigma, this R direction, just rescaling 2/3, just multiply 2/3, and then so 11-dimensional supergravity action reduces to this guy. I'm not going to write down everything. It's just rewriting. Just put everything into the 11D supergravity action, which I already erased. Then you can derive this action. It's a very tedious exercise, but one can do that. But the one thing one should notice that and also, so the relation between kappa 10 and kappa 11 is given by as follows: 2 pi 2 kappa 11 square is given by e to the minus 2 pi given by 2 kappa 10 square. So if you write down everything in terms of the supergravity action, 11D supergravity action in terms of this field I have written here, and just compare the coefficient. Okay, compare the coefficient. Then you can relate kappa 11 and kappa 10 in the following way. Then this will give you the relation. So you just plug into, this is written by Planck length, this is written by string length, and therefore you can just relate between them. Okay, so from here, one can just relate how should I write down? R over LP cube is equal to G string e to the phi square. Right? I'm correct, right? So this and e to the phi will give you the string coupling. So that the expectation value of the dilaton field gives you string coupling. So therefore it becomes G string square. And then, so we just substitute this one into here, and then you will get 2 pi r divided by 2 pi LP to 9. I just plug this 2 kappa 11 square is equal to 2 pi over this guy. Okay. So just the left hand side becomes like this way. So because the kappa 11 is written in terms of string Planck length, and since the e to the minus 2 phi is the string coupling constant, so you get the GS square 2 pi LP and to the 8. So this will give you the relation between Planck length and the string length. Planck length, so this will give you the relation between R divided by LP. Unfortunately, I cannot write down here, so then let me write down here. R divided by LP cube is equal to 1 over LS squared. So this is the relation between Planck length and string length. And R is the circle complication, the radius of the circle that is used for complication from 11 to 10. Okay, so now you have to relate two relations. R divided by Planck length equals string coupling constant, and R divided by LP cube is written in terms of the string length. Therefore, if you combine two results, at the end of the day, we get the following. The radius is given by GS times LS. It's a very simple result. The reason why we did some very weird scaling between this sigma and phi is to get this simple relation. I mean, it looks like a bit weird to scale sigma by 2/3. I mean, it's just a rewriting of this the metric here. The sigma is the same as phi, just up to some factor. But the reason why we did that is to get this simple relation. If you want to solve the relation between string coupling constant and Planck length, and also kappa 11 and kappa 10. Okay, so that's how you obtain the 10D 2A supergravity from 11D. Okay. And then we will move on to 2B. 2B, so you need to do the T duality. You have a very similar action with 2A. So let me write down. So here you have 11D supergravity, and 2a. Okay, so you just circle on S1. If you do the circle complication, you can look at the at least massless spectrum. And we know this is their related T duality. So we just need to do a T duality and a supergravity action. Okay. So okay, so maybe I should tell you, so what are the massless field of type 2b? Type 2b, type 2a massless field. So let me write down massless field. So let us recall type 2a massless field. Maybe recall, just recap what we have learned. So 2a, so NS sector is the so we should do the same thing. And 8s and 8c. As far as remember, I hope I'm not wrong. Yeah, it should be the case. Let me check if I don't make a mistake. Hopefully I don't make a mistake. I think my lecture note I call it is C and S. And from here you get the NS sector, and then here you get the Ramon. Okay. So that's the bosonic field, and you have a Grapptino MATLAB, and also the Latino. I already forgot. And also the similar thing. You have, since you have 32 supercharges, you have 2 copies of them. I forgot to mention the notation. I call it plus minus and minus plus. Plus minus and then minus plus. And 2b, so these are massless field. So that everything written in the action over there is written everything in terms of massless field. So we just only look at the bosonic part, but the corresponding fermionic part, which is super complicated. And 2b, you have a 8b, 8s, 8b, and 8s. Okay. And G, E, 5, the same thing. And you have, what do you have here? Do you remember? Am I correct? Yeah, I think I'm correct. Okay. So this Ramon field, that is coupled D-1 plane, D1 brane, and D3 brane. Okay. D3 brane, and then the fermionic part. I'm not going to write down fermionic part. So we are going to write down everything in terms of these massless field. It's very similar. It's similar to that one. Unfortunately, I have already erased. So, S type 2b, S is given by 1/2 copper times square. I mean, it's just the same thing as is type 2a. Just and S sector is the same. Oh, I omit e to minus. And this is the same, as you can easily imagine. then, of course, type 2B Ramon is different from type 2A. And then you have kinetic term. And also you have a transonic term. Oh yeah, thank you very much. I don't know why I keep writing plus. And then you have the transonic term. It's almost same, but you have C4, which H3, which G3. GI is indeed GI is the field strength of Ramon flux. CI. Okay. O plus 1. Thank you. Oh yeah. And then also G tilde I plus. Okay, maybe I should call I and I minus 1. GI tilde is just shift of GI. Okay, I think I should write down independently. Yeah, I think I should write down independently. Otherwise, I cannot write down. It just shift. I mean, if it is G3 case, this guy is just a shift of G by B field and so on. BH2, sorry. And then okay. Remember that this C4 plus, well, the reason why plus is called that the G4 is self-dual. Where should I write? Like this. So G4 is G5 is the self-dual. It's a self-dual under Hodge star. So it's 10 dimension. So the 5 form can be self-dual. Okay. Which one?
Second terms coefficient.
Instead of 3 times. Okay, thank you very much. Self-dual condition. Oh, I think tilde is missing. Sorry, tilde. Okay, so this is coming from self-duality condition. Okay. So it's very similar. So the bosonic action is NS vector is just the usual one. Einstein Hilbert action. So this is that appear even bosonic string. Right? Do you remember? When you compute Wall symmetry and so on, yeah, Wall anomaly, we derive the graph. So you can just take a look at the section of Wall anomaly. And if you compute beta function of G and so on, this is the same as the equation motion of this action. So it's the same. So the NS part is the same as bosonic supergravity action. Instead of In bosonic, it's instead of 10 dimension, you have a 26 dimension, but it's the same form. But for superstring, you have to add the kinetic term of the Ramon field and the Chern-Simons term. Yeah. The Chern-Simons term a bit more complicated in 2B because you have 3 Ramon field instead of 2. So it's a bit more complicated. Okay, so these are supergravity, and of course, so I just there's a T duality and type 2B supergravity, and you can do the oriented for the projection omega, and you can just have type 1 n equal to 1 supergravity. You can have n equal to 1 supergravity, but which I'm going to omit. In n equal to 1. Yeah. Sorry, it's n equal to 1. Maybe. I mean, these two really come from n equal to 2. So these are the supergravity, the really crash course of supergravity. I mean, I can also write down the supergravity type 1, but not type 1, n equal to 1 theory, but I'm going to omit. It's very similar. You have the NS and Ramon, and then Chern-Simons. It's very similar, but the number of supersymmetry is reduced. Okay. Then I want to keep type 2B action. And this type 2B supergravity action has a very nice property. And then I'm going to erase. Yeah, I think I need to erase. So here, in bosonics action, so in the Y anomaly, so we just see the equation motion of this one is the same as the vanishing of beta function. Equation motion of this action is the same as vanishing of beta function of G and B and phi. And then that is based on perturbation theory. It's just one loop determinant. Just computing one loop determinant, and you derive that. That is perturbation theory, and we would like to know what's going to happen from now when GS is going to be very strong. No longer. So we assume GS is very small, so that you can do perturbation theory. But now we just growing to the peak, the strong. Then what's going to happen? So we will write down this type T to be actions following way. And then, so you just scale the metric by diatom field. And then also, introduce some, it's called axial dilaton. It's called axial dilaton. C0 is sometimes called axion field, and phi is we know it's dilaton. It's axial dilaton field. We call it tau, and then so we just write down. So if you look at the massless field, you have the B field is two form, and you have a Ramon two form. Okay, so you have a two form. So that you have a 2-3 form. Yeah, G3 and H3. H3 is the field strength of B field, and G is the field strength Ramon field. Now we will put the equal footing. So F is the you just put the equal footing of these three form. Okay, and also some rewriting of this axial dilaton field. Yeah, I mean here you have a 0 form and 0 form. Okay, it's very similar. So you just write down the following way. And then magically that action, the complex action, can be repackaged in a much more simpler form. The action can be written in terms of very simpler form. It's 1/2 kappa 10 square into x minus GE. And transonic terms also become much simpler. Or more transparent. I mean, this is reform. So E is equal to -1, 0. Okay, so this transonic term corresponds to here, and then this F and F corresponds to essentially this guy, and also that guy. This guy. Okay. And then this axial dilaton corresponds to this guy, and then this guy. So since both are one form, so it's very similar. So C0 and phi are 0 form. The field strengths, kinetic field strengths, you can just repackage using this tau. So it's a very huge simplification one can do by just repackaging the same 3 form and same one, 0 form here. And then the following symmetry become manifest. Oops, I erased, sorry. I hugely admire supergravity people. I mean, it's a huge, tedious work one has to do to get this kind of a symmetry. linear form of as you have done in an exercise in the homework. Where lambda is equal to dCBA in SL2R. So the reason why I put tau here is tau really look like upper half plane, and SL2R really acts on the upper half plane. Okay, as you already seen in the exercise. And then so so DCB. It's a bit weird way to write down the SL2R. You just hit ABCD, but to make everything symmetry manifest, you have to write down and rewrite a bit strange form. Okay. And then so GE metric and the full form is invariant. On the SL2R. So this is the symmetry that appear once you rewrite type 2B action, type 2B supergravity action in terms of tau and F. And somehow this lambda SL2R action just mix C0 and e to the phi and H3 and G3. And let me erase. So remember that so what are the fields that couple the C2 and how? Oh my goodness, it's a B2 and C2. So essentially D is equal to that one F, right? F3. What are the object that is electrically coupled to B and C? B2 and C2. What are the objects that couple to B field? Yeah, so it's the most fundamental one. So B field couple for string. That's why B field always appear from the bosonic string. It's even first lecture, the B field appears. So it couples the fundamental string. And so what couple to the D2? C2, sorry. Electrically. It's a D brane. D1, good. What is the magnetically coupled this field? Magnetic dual of fundamental string is what? It is 5. So these are electric coupled to BC and also magnetic area BC. So this one is rotated by lambda. Indeed, this lambda over there. And then to impose, so the one thing we missed is that we didn't impose the Dirac quantization condition. Indeed, if you introduce Dirac quantization condition, which is the mu d minus 6 is 2 pi integer. I think it should involve some kappa. As for kappa to the, I already forgot. Kappa 11 to the some power. I already forgot. Yeah, kappa to the, no, 10, sorry. 2 kappa 10 squared. Okay. So kappa 10 is string length, so this is Dirac quantization condition should satisfy. Okay. If you impose this condition, this lambda is not shouldn't take as a 2r. Instead of these numbers should be integer value. So therefore, true symmetry of type 2b string theory. So it's a supergravity action. Okay? And if you quantize the supergravity, you get the string theory, and that we enjoy SL2C. Okay. So this tau can be understood as really a complex structure of the torus. So tau is, and this SL2Z can be understood as the mapping class group action of the axial diatom field. And in particular, so if you look at the S element minus 1, 0, 1, 0, okay, and look at tau, what's going to happen. So we'll map tau goes to minus 1 over tau. That's what we know. Once you set for simplicity, once you ignore C0, this tau goes to minus tau is really G string coupling goes to 1 over G string coupling. So it's a weak coupling region go to strong coupling region. Okay. So e to the phi is the really the string coupling, so as we know. So there's expectation value of diatom field is string coupling. So therefore S duality is really strong weak duality in type 2B. Okay, so if you use this action of the S duality, so one can just go from a weak coupling region to strong coupling. So this is a remarkable duality. And furthermore, so that's type 2. It's a bit detour, but since the Wang Hao is doing really such kind of research now, anyway, I mean, people, I think only think people who use brain in this at Fudan, I think I only ask in my group. For instance, if you have the NS5 brain, and D3 brain, and then you have a bunch of D5 brain, you just consider such configuration. And there is a fundamental string stretch in between, and the formula F1. Okay. And then this will generate so-called 3D n equal to 4 SQED. If you take S-duality, and then use, I'm not going to explain in detail, it becomes like this way. So this D fibrane becomes NS fibrane, and the NS fibrane becomes D5. So as I mentioned, NS5 becomes D5 by S-duality. D5 becomes NS5. The same thing happened. D1 becomes F1, F1 becomes D1 by S-duality. Just swapped. And the configuration becomes like this way indeed. So this NS5 becomes D5. Okay. And D3 brane stays the same. So the D3 couple, electromagnetically coupled to the C4 plus. So D3 stays the same. Okay. So D3 stays the same. And this D5 becomes 3NS5 brane. 3NS5 brane. And since we know that from D brane, you have a gauge field. You have a D brane. If you have a one D3 brane, you have a U1 gauge field. This is U1. Okay, U1 gauge field, and you have the D5 is fixed and heavier, so it becomes some fundamental matter. It coupled to it charged under gauge field, some matter, as an electron and so on. And then this configuration, you have this NS5 suspended, D3 brane suspended by two NS5 brane, you get the U1 gauge field. Okay. However, another U1 will show up from D3 brane suspended by NS5. Okay. And you have the fundamental string. Okay. That will give you matter. Okay. You have a two. By S-duality, by performing S-duality, one can cook up so-called two quantum field theory. And this, they are related by, so they're actually duality, mirror symmetry. Coming from S-duality of type 2B. So there are different quantum field theory. So it's a U1 gauge field, and there's 3 electron. You have a 3 electron, also a 3 boson. It's a supersymmetric. You have a boson fragment. On the other hand, you have a 2 gauge field, and you have a fundamental only one electron coupled to one U1 gauge field, another electron coupled to another gauge field, and there is some bifundamental appear. And in fact, they're different description of the quantum field theory. But if you go to its QED and it's go to IR, and in fact they flow to the same superconfig point. So that the partition function should match. So therefore, using this S-duality, one can cook up some very non-trivial duality between quantum field theory. Okay. And this was already, this is first common integrated cyber. also, I don't know, bunch of people. What's the name? Around 96. So the SDRT swap NS5. I should write NS5. Swap NS5 to D5. Oh my goodness! Why did I include this guy? I mean, that's also true. I'm sorry. This brain diagram really comes from Hanani-Witten. Sorry. It's called Hanani-Witten transition. I'm sorry. I think instead of this, anyway. So this is heliocentric perspective. This Hanani-Witten is more like a brain perspective. Okay, let's take a break. Oh. Today I brought something. We can have it. Yeah, you can open and please distribute to the other student. Okay, enough.
做推断这个东西，然后有算这个东西，然后克，然后克。
Can you open the window? The window. Yeah, thank you.
算一个东西吗？回头这个人如果看你飞枪的话，被选中的孩子，是很一般教练。就是报编那个差远了。一天大概是4分钟，一个3000一说。条件它是死干了，但是你打一周的时候，它是死不。它是有最后一个月，对其他月份生存没有压力，就最后中间嘛，就是温度会降下来。但是你的装备就保留。
So do you guys start solving homework? Not yet. I mean, if you haven't, you should. I mean, problem 2 is not so easy. Problem 2 is rather difficult. I mean, it's kind of advanced problem, so you have to, yeah. Spend a lot of time. Okay, shall we start? Okay, so we talk about the stronger coupling limit of type 2b string theory. Then the summarize is the where did I put choke? Huh? The summary is the so the S duality will swap these guys, but these three stay the same. These three soft L. That's why it is safety. These it is safety come from Lagrange limit of these three. And it's 3D for the -4 enjoy SL2's invariant. That's another way to see anyway. So we will see the same same phenomena for edit safety. Okay. So type 2b. So we just look at the from weaker coupling and stronger coupling limit. So let's look at the stronger coupling limit of type 2a. So recall that the type 2a can be obtained by this convocation of 11D supergravity on the on a circle with radius r. So recall what we did is 11D supergravity, and then on S1 compactification, you get the 10D type 2A supergravity. Moreover, radius r is related by G string coupling times string length. So if G string is very small, radius very small. Okay? But if you take the G string very large, type 2A is somehow, so this is the, of course, this is the low energy limit, low energy effective field theory of the 2A string theory. So low energy effective theory, just look at the massless sector, and you just integrate all the massless massive mode. So this string suggests that, and this one is actually weaker coupling limit of, can be understood weaker coupling limit of string theory. If you take the stronger coupling limit, GS, you have an 11-dimensional string theory called M theory. Stronger coupling limit of string theory is not understood at all. Nobody understands M theory. Even I mean, even though there are lots of developments, but if you assume this theory, you can explain lots of things. And in particular, so we know that the supergravity has the three form. So recall that this supergravity has this supergravity has three form, and the gravity. Okay, these are bosonic field. So there is no B field. Okay, so all the supergravity 2A and 2B have a B field and a diatom, But now dilaton becomes some participator radius R now, and then there's no B field. Okay, B field is coming from dimensional reduction of M3 indeed. So there's no string. So, but we need some object that couple to M3. This massless 3 form. And then, so within, so this is the within famous focal is 95. I mean, the video is, so the talk is string conference of 95 within the famous talk, and which is even available on YouTube now. I mean, it's worth looking at. And also, the paper by string theory, string dynamics. And something. I already forgot the name. I should have known that. I already forgot. String dynamics and duality? Something like that. I already forgot. I should have known that. So it's string form. It should couple the like a two spatial dimensional object, and we can call it M2 brane electric couple to M3, and then magnetic plane couple to. Now, I mean, recall that the so here you have a 1 plus 5 is equal to 6, okay? And there, electric couple to the C0, and then this is magnetic couple to C0, okay? And these three couple to the electric and magnetic couple to the C2. And this is type 2, and you have D2 and D4, and D0 and D6 in type 2A. So these are electric coupled to C minus 1. This is electric C1. Yeah, C1. Am I talking something silly? It should be, yeah. C minus 1 is C1, and magnetic coupled to C1, and then magnetic coupled to C minus 1. And if you add them up, you always get the 6, right? However, so we now move to the 11th dimension, so that the electric couple and magnetic couple, if you add the spatial dimension, you get the 7. Okay? So the number of the dimension increased by 1. Because we move from 10 dimension to 11 dimension. Okay, so M3 is somehow strong that appear, and a stronger couple limit of the string type 2 string theory, and somehow once you take the string couple limit, somehow another dimension will emerge. Okay, That's called M theory, and it has a two object, M2 branes and M5 branes, and then the following thing with so tension mu M2 is equal to M2 brane charges is Q, and M5 brane charges is proportional Planck length. Of course, the 3 is 2 plus 1, and the 6 is 5 plus 1. So if you assume this one, everything is consistent. So the M theory, M3 and type 2A, so you just reduce by on compact form on S1. Okay. So then the Kaluza-Klein momentum of the brane is proportional 1 over r. So we know that the classical line momentum is proportional to 1 over r, and this is indeed 2 pi r. Sorry. Oh, okay, sorry. So this is 1 over r, and this is equal to 2 pi over gs 2 pi ls string. Okay. That is related to here is d0 brane. So type 2 and d0 brane can be understood as the classical line momentum of M theory. So recall that R is equal to GS times L string. And then, so what about D2? Type 2A, you have a D2. So, oh, sorry, before D2, I think it's better to, so this is dimension 1. So M2 on S1. Sorry, this is KK momentum. KK momentum. Is indeed, so you just have a 2 pi over 2 pi LP cube. So this is the M2 brane charges, but you just compact from S1, so you just multiply 2 pi R. Okay, so it can be understood tension of the M2 brane. So you have a circle complication with radius R, and M2 brane wraps on this circle. Okay, wrap on circle. Then tension or charges or mass is proportional to the length of the circle. So you just multiply 2 pi R. So it's length of the circle on a string M2 brane tension, and then you get the F1 is the charge of the tension of string tension. You just get the string tension. The string tension. So that once you compact M2 brane on a circle, in 10-dimensional perspective, spatial dimension becomes 1 dimension. So 2 reduced to 1. The M2 does not wrap on circle, it's just a 2 pi, and then 2 pi LP, and then Q. This, if you write down, in terms of string length, 2 pi LS to the cube times GS. So recall that we have the relation between LS and then LP in the first part of the lecture. So we just recall that the GS LS divided by Q is equal to 1 over LS squared. Okay? So therefore, Planck length can be written the string length like this way. So in other words, 1 over LP cube is equal to GSLS cube divided by 1. Okay. So I just rewrite Planck length in terms of string length and string coupling constant. So this is tension of the charges of the D brane. We will see. And the same thing happened. So you just have M5 brane on the S1. You have 2 pi R time divided by 2 pi LP to the 6. Okay. So now you just multiply string tension of M5 brane times the length of the circle. Okay, circumference of circle, and then you, of course, you just compact from S5 over M5 brane, and then what you get is what? What would you get? D4. So D4 brane. So the spatial dimension, if you 10-dimensional perspective, 5 reduced to 4. Okay, and then just rewrite everything in terms of LS by using relation between this one and that one. And then what you get is indeed 2 pi gs 2 pi. Okay, now, so their electric object and this magnetic object, if you multiply different charges, what you obtain, you should obtain this guy, okay? So let's look at it. So if you multiply them together, together, you get the 2 pi gs 2 pi times 2 pi gs 5. Okay. And then, so recall that I hope I don't make a mistake. This can be tricky. What is the copper 10? Copper 10 is what? It should be, yeah. Hopefully, what was copper 10? I already introduced today's lecture. Where's copper 10? Oh yeah.
I think it's 6 minus 8.
Huh?
This Dirac quantization.
6 minus 8. Yeah, exactly. Thank you. 6 minus 8. Yeah. So now I just put the d equal to 2 and d equal to, so it becomes d4, right? So d4 d2 and d4. And the 2 copper 10 square I just introduced today is indeed, where was it? My lecture note, where did I write? Oh yeah, so here you have a 2 pi ls to the 8 divided by 2 pi, right? Okay, then what we are going to do is it becomes the 2 pi divided by 2 pi ls cube it should work. So you just multiply, you have a 3 plus 5 is 8, 8. And then 2 pi gs square. Okay. 2 pi gs square. Okay, I think I missed gs square, I guess. And this is equal to 2 pi. Okay, up to string coupling constant, it's okay. 2 copper. 1 over 2 copper and square. Okay. So maybe I may miss gs square somewhere in the normalization, in the lecture notes. Stupid. Sorry, I think. Let me think. There is again type. Okay, I think for timing, let's normalize in gs square for time being. Then this will satisfy. Okay, you can understand. So you just multiply this times. So this is equal to mu d2, mu d6, no d4. If you multiply them together, you have a 2 pi divided by this guy, so this guy. Then it satisfies the direct quantization condition. Seems like I missed somewhere in GS square in the lecture note. Sorry. I will correct in lecture note later. I think I made a mistake in summary normalization. Okay. If you properly normalize you should get the right direct quantization condition. Okay, and then let me move on. So M5 does not wrap on S1. You have 2 pi LP to the 6, and this becomes, as you can easily see, it's there magnetic, electric and magnetic object. Electric objects becomes F1. Magnetic objects should be NS5. And then you just write down everything in terms of this relation, using this relation. So then you have a 2 pi divided by GS square, 2 pi, like this way. And again, so if you just look at the modification of this guy is the same as modification of this guy. Okay. Right? Yeah. So GS square and 2 plus 6 is equal to 8. So 3 plus 5 is equal to 8. So they are electric objects, magnetic objects. You can see. And D6. Sorry, no. D6 is a much more complicated one. So as you can see, D0, D2, D4, D brane is 2 pi over 2 pi ls to the some 1 plus spatial dimension times GS in the dimension. So therefore it should be 2 pi GS 2 pi 2 pi ls to the 7. This is a bit more complicated one, indeed. So this is called colored cycline monopole. I mean, I'm not going to explain 2 pi r to the square, spherism square, 2 pi LP to the 6. It comes from actually geometry. I will explain briefly. The string theory it's a bit complicated one. It's some kind of magnetic dual of cycline momenta, but geometrically, so if you put M theory on a so-called top knot state, it's a hyperkähler manifold. It's locally, it looks like a R2. The fiber is Seeger. At each point, you have the S1 compactification. Let's see. Yeah, sorry. So M theory on tab knot. Tab knot is 4-dimensional object, which can be understood as the R cross Seeger. Locally, tab knot can be understood, roughly speaking, R2 cross Seeger. cigar is this kind of object. And you just compactify on the S1. And times, let's see, R7? How did it work? Sorry. Let's see. Yeah, it's a bit complicated. So if you compactify on the cigar, it becomes the following way. So it's as compactify on cigar. How did it work? You have the R2 cross R plus cross R7. Yeah, R7. So if you compactify on cigar, you have, yeah, now I remember. So if you compactify on cigar, the M theory on cigar, you have the R plus direction up here. But there is some, the boundary condition should appear, boundary appear. If you compact on, in the tip of cigar, you have a boundary of R plus. So this R plus is 0 starts in the positive direction. Okay? And then D6 ring wraps on here. So this type 2A, this is M theory on top not cross R7, and the D6 lives on this R7. So D6 is 1 plus 6 dimensional object, so maybe I should put the 1 plus 6. And then it sits on the origin. Sits on origin times origin. Origin means here. Origin here. So the D6 plane appears in typical cigar, indeed. So D6 plane appear indeed the geometrically how you compactify on the M3 in some nice space. It's called hypergala manifold. So this is given Hawkins. Given Hawkins, find the metric Hawkins. Now space. It's locally look like R2 crumb cigar, and so if you compactify and fiber on the circle on a cigar, you get the R2 cross R plus, and on the tip of cigar, you can just create D6 plane. So that's how you create the D6 plane geometrically from M5 ring. No, M5 ring, M3, sorry. Yeah, but I'm not gonna explain how more detail. I mean, it's yeah, it's difficult one, but so if you assume the existence of M theory at the strong coupling limit of the type 2A, and you assume the existence of M2 and M5, that couple the massless 3 form, and everything, all the object in type 2A can cook up from an out of M theory. Out of M theory, so that the so that's what Witten proposed as the stronger coupling limit. Strong coupling limit of the okay, so the stronger coupling limit, strong coupling limit of type 2A. And if you go to, I mean, how to say, the radius is small, depending on how you wrap M2 brane, where M2 and 5 sits, you can create all the extended object in type 2. And then, so M2 brane, so D6, D brane, DP brane, people know so what kind of theory living on. So it's a Yamil theory living on here. Super Yamil theory living on DP brane. But people didn't know, like, when the Witten proposed what kind of theory living on this D2 brane. And then, so M2 brane, M2 brane. There's a breakthrough by Bagger and Lampert and Gustafsson. And also, you might have the AVGM, Aharoni, Bergman, Jefferies, and the Madasena. Jefferies. So this is some kind of, it's 2 plus 1 dimension, 2 plus 1 dimensional, or 3D dimensional, highly supersymmetric, n equal to 6 or higher. Some exotic supersymmetric some like a Chen-Simons theory. Also, you have it should have Yang-Mills, right? Yeah, it should have a Chen-Simons and Yang-Mills. You have both action. As you know, F which star F is the Yang-Mills and the Chen-Simons A plus 2/3 A cube. You have to combine both the action, and you have to supersymmetrize. And if you want to supersymmetrize, you have to. N equal to 6, it's a very like you need to use some kind of special supersymmetric, very weird special supersymmetric transformation they found. This Bagger-Lambert found a very exotic supersymmetric some kind of bracket you have to use. But anyway, so and then they consider ABGM also generalize it and also study the large n limit. So they study, so it becomes IR is a superconformal, so it brings to ADS 4 CFT3 correspondence. They also study ABGM study. For M5 brane, is much more difficult. I mean, there are many people. I mean, nobody has understand this one. There is no Lagrangian description. No Lagrangian description that we know. So no Lagrangian description because of this self-deal two-form. But many things. So if you use the so-called string reality, also if you use the compactification and fiber on the manifold, of M5 brane on some manifold MD, one can obtain lots of quantum field theory. I mean, there are many people working on here. Gaiotto, Gukov, company. String duality. Anyway, so these are just famous people I just listed. Buffer. Too many actually. Buffer, Morrison. Too many to list. Tachikawa. Even Korean group, the Kim, Kim and so on. I mean, it's unfair to list only this name, but lots of people. Even nowadays, it's working. People are working. So it's a hot topic. I'm also partly working on this kind of subject. But it's still a mysterious theory, but lots of interesting phenomena can be found, and it gives a lot of new insight in quantum field theory and string theory. Okay, so that's the M theory. So now we briefly cover 11D Supra. I don't know how many times I've written this diagram. And then M3. So we know they are related with T duality. And this is orientable projection. And type 2A is compactation on S1. Or maybe on S1 from M2 is like this way. On S1. And now, we would see what's the relation between type 1 and the heterotic. So from now on, we will see the relation between type 1 and heterotic. And next is this one. Next is this one. So that's what we're going to see. I think first I'm going to see from here. Sorry. From here. And next is this one. And after that, I will talk about the strong so the question, what is the strong couple limit of a heterotic and so on. Any questions so far? Sorry, I think type 1 supergravity action will show up later. Sorry. I think okay. So T duality. So last time I talked about heterotic string, and then so there are two constructions. One is bosonic and the other is fermionic. The bosonic construction we have used modular invariant partition function so that the this gamma dd has to be self-deal and even, and then 16-dimensional Euclidean lattice. D equal to 16, right? As far as remember. Okay, 60-dimensional self-deal lattice. And so we know that this one had there's only two candidates. So root lattice of gamma E8 plus E8. Yeah, I mean E8 cross E8 and weight lattice of gamma SO32. In order to not to make a mistake, let me check my lecture note. I didn't print out that part today. Hopefully I didn't make a mistake. Root lattice of E8 cross E8. Okay, good. Yeah. Good. Okay, so D equals 16, and then yeah. So now, so once you compactify heterotic O on S1, so we know that the type 2B and type 2A are related by, if you do the S1 compactation on radius R and S1 compactation, you get the same theory. We already know. One over R, alpha parameter. So it's a T duality. If you compactify on S1, so it's 11-dimensional and 10-dimensional, and all the spectrum, string spectrum and so on, coincide once you compact on R and alpha over R. So that's T duality. The same thing happens indeed for heterotic O and heterotic E. Once you compactify on S1 R direction, S1 alpha prime over R, the radius, it becomes same theory. Okay. So to see that I mean, it's a very, very ad hoc. So I'll be a bit pedagogical and then very ad hoc. So we know that the lattice of this gamma SO32, and you just lattice of 32, and you just have another lattice 1, 1. So again, if you compactify on a circle, so heterotic string is how to say? Right moving sector is the superstring. Holomorphic or right moving superstring, 10D superstring. It's right moving, and the left moving is the D equal to 26. Bosonic string, as you recall. And the compact one on 6-dimensional manifold, okay? So 6-dimensional torus, okay? And lattice gamma D comma D equal to 16-dimensional lattice this is PL. Lattice coming from PL, and this coming from PR. Recall P. So you have a counterclockwise momentum or winding mode. So you just combine them together, PL and PR, you get the D comma D lattice. That's what I have explained last time. So now, hydraulic, you find a compact phi on S1. You find a compact on S1. Okay? And then boson, if you only look at the bosonic part, it's the same as compact from 17-dimensional lattice. Okay? 70-dimensional torus. Okay? If you compact, it's equivalent. So therefore, you have to add one more dimension to the 1,1. The one more dimension. That is 1,1. And this is indeed, you have to do the same thing for E8 cross E8 lattice. And you just add 1,1. Indeed, this is, it's a mathematical theory. If you add the some lattice, high dimensional, and it becomes 5-dimensional lattice, lattice structure becomes the same. Indeed, it's a bit too ad hoc, but let's accept this one is a mathematical fact. And then, so as you know, so the modular space of the torus, for instance, torus, the modular space of torus can be understood as the upper half plane divided by SL2Z. Okay. So the similar thing, one can just consider so here, so this one is unique, unimodular, even. So you have a even and the unimodular, so and the Lorentzian lattice. At 1,17. So this is only one lattice you can have it. And then you can just have the modular space. You can consider modular space of lattice, so-called the Narayan lattice. So which appear in this homework problem too, or 1,17. So it has the large gauge group transformation divided by 1,17. So these are Lorentzian group. O1 is just Z2. So modulus of this lattice can be understood as follows. So this is just O group, and I'm not going to explain something about the modular space, but so you can just use the fact that the So the theory equivalent theory compaction S1 of the heterox O HO compaction S1 heterox E corresponds from the compaction S1 can be it follows from this mathematical fact. So if you add one more lattice, M11, the lattice structure is the same. And then if you look at the modular space of this lattice, you can get some massless mode of this. The theory living on here. So in the torus case, so in torus case, modular space of torus is indeed modular space of genus 1, which is actually upper half plane divided by PSL 2Z. Okay. 2Z. So that will give you lattice structure. So you have sorry, my hand drawing is bad, pretty bad today. And then you have, okay, so this is the modular space of torus. And at each point, you will give a lattice structure. So you start with this, so you have given a peak point here, you have a lattice structure. You have a torus. Okay, so this is tau lives on here, okay? So given a point, you have a lattice structure. So it's a similar thing happening in here. So given a lattice, Lorentzian lattice that satisfies this condition, even unimodular Lorentzian lattice, one can also ask what kind of like complex structure or the shape of this Lorentzian lattice. And this is called the shape of lattice is called modular space of this Lorentzian lattice, and this 1,17, maybe 1,17 modular space is indeed this guy. And this is called a Narayan modular space. So this is called Narayan modular space. Indeed, this is 17. So pick a point in this huge modular space, you have a one lattice with fixed shape. Okay. It's a very huge generalization of this torus case. Given a peak point on the modular space, you have one shape of lattice. Okay. The same thing happened here. So given a point in this, its coset group on the modular space, you have a fixed lattice with fixed shape. So therefore, once you pick a point here, you can have one compactation. At some point, if you pick the boundary of this, so if of course this guy is Lorentzian. So it's a non-compact group. Okay, it's non-compact group. So therefore, there is some boundary and a singularity because of this, as you can easily see. So if you look at this one, there is three singularity. One is the infinity, tau goes to infinity, I infinity, and another is this point, another is this in the middle point. Okay, these three are singular point. Okay, and if you go to the weakly coupled left, okay, so tau goes to I infinity. You have the bound. You can see the boundary of modular space. There is such a thing happen here. If you go to some particular boundary of the modular space, you have some decomposition. But for generic point, everything decomposes. The gauge group is decomposed. You want to the rank So it's for generic point of modular space. At generic point of modular space, this 1,17, the gauge group is broken to U1 to the 18. Instead of E8 cross E8, and then so this is the rank of the, and at some point it becomes, it gets enhanced. It gets enhanced, something like so SO32 2 times U1, or it sometimes at boundary of modular space it becomes E8 cross E8. It's a bit heuristic in this argument, but you can see that for instance, if you look at the type 2A, so here, when you set R is equal to self-additive radius, U1 gets enhanced to SU2, right? SU2. That we already seen. We have already seen that. So the similar thing phenomena will happen. So if you look at the some particular point on modular space, the gauge group gets enhanced too. But a generic point, everything is broken to U1 to the 16, and then the theory looks the same. So it's a bit heuristic. That's going to be important. And then if you compactify, instead of S1, you can compactify heterotic on the heterotic string on T, then it becomes, everything becomes D plus 16, D, and then D plus 16, the modular space of D, and D plus 16. And this modular space will show up later. So this becomes D and D plus 16. And this Narayan modular space will show up later. Of the show up later to show the heterotic DT4 is the same as 2A on K3. It's very magical on duality will show up. This is actually already predicted by Witten's paper as the original paper, but the more precise case is Morrison, Aspin or Morrison. Anyway, so it's a bit heuristic, but if you compact from S1, lattice structure of the gauge group becomes the same, and the modular space will become important to see the duality later. Okay, let's stop here, and the next time I will talk about this part. I already erased. Type 1 and heterotic duality. Yeah, let's stop here.